Now let's have a look at real quiz number 12. Question number 1 talks about scaling Mount Everest. Base camp at Mount Everest is an incredible elevation of 5,300 meters, which is about 4 kilometers higher than we are above sea level. The peak is even higher at about 8.8 kilometers above sea level. The climb from base camp to the top of Mount Everest often takes upwards of 2 months. 300 people have died trying to make this climb or the descent. On one particular climber has a mass of 75 kilograms and is able to climb from base camp to the peak of Mount Everest in 5.25 days. Whew, there's quite a bit to that. We're going to find the work done by a 75 kilogram climber as he climbs it or she climbs it in 5.25 days, assuming that the climber starts at base camp and ends at the peak of Mount Everest at rest in both cases. Kind of like when we climbed up the stairs, did our little power example running up the stairs last week. Let's take a look here. If we're climbing Mount Everest from base camp to the top, to the peak of Mount Everest, that means we've got an initial height of 5,300 meters. We've got a final height of 8,849 meters. The mass of this person that's climbing is 75.0 kilograms. And we've got a time interval here. Not that it really matters for question A, the work, but it is going to matter for the power output in B. We've got a time interval here of 5.25 days. Now, there's 24 hours in a day. There's 60 minutes in an hour. There's 60 seconds in a minute. So we're going to multiply 5.25 times 24 times 60 times 60 to get the number of seconds that it took this climber to scale Mount Everest. It gives me 453,600 seconds. We're looking for the work. And of course, in B, we're also looking for the power output here. Now, just like our practice quiz yesterday, we're allowed to try F times D. I don't think it's going to be very useful here for me because I don't see a D or an F. The alternative to that is to say W is equal to delta E, the work energy theorem, the final energy minus the initial energy. In this case, the final energy of this climber isn't kinetic, like it was in the practice quiz yesterday. The final energy is potential energy, gravitational potential at the top of Mount Everest. Even at the base camp, this climber has potential energy. The initial energy is also potential. So let's sub in our numbers here. 75 times 9.81 times the final height, 8,849. Subtract the mass again, 75 times 9.81. Realistically, gravity is going to be a little bit less than 9.81 as we scale Mount Everest. But that's the number we're going to have to use, close enough. 9.81 times 5,300. And once again, just like yesterday, we can't cancel the mass. Even though it appears in both terms on the right side, it doesn't appear at all on the left-hand side. We calculate those two numbers, we subtract them, and we get 26,11176.75 joules. We want to round this to 3 digits. So let's look at the 4th digit. It's a 1. Therefore, the 3rd digit rounds down. 2.61 times 10 to the 1, 2, 3, 4, 5, 6. 2.61 times 10 to the 6 joules is the amount of work that this climber does as he or she climbs Mount Everest. Now the power, these are always easy, right? The power is always easy once we get the work. We just take whatever work we found and we divide it by the time. So we get 26,11176.75 joules divided by the time interval here of that big time of 453,600 seconds. And we calculate that one, it gives me 5.76 watts. Seems like a pretty low power. If you went for a run, your power output might be 175 watts, 200 watts. But remember, we're climbing Mount Everest. It's taking us 5.25 days. We're not running at the same speed and power output up Mount Everest as we would be if we were running on the track or down to the dog stadium. 2. In a stunt on a movie set, a 1,500 kilogram car drives off the edge of a 10-meter high cliff. Don't know what direction? Doesn't matter, because we're only looking for the speed of the car, not the direction. when it's 2 meters from the ground, and then when it hits the ground. So our givens again, my mass is 1,500 kilograms. My initial height is 10.0 meters. And in question A, my final height is 2.00 meters. We want to convert that 36 kilometers per hour to meters per second. VI, 36 times 1,000 to give me meters. 3,600 on the bottom gives me seconds. Ends up giving me 10 meters per second. 36 times 1,000 divided by 3,600. Looking for VF here. So we're going to say EI equals EF. Again, we got kinetic energy at the beginning of this, at the top, because this car is moving. It's also got potential energy because it's got a height of 10 meters. It's got kinetic energy when it's 2 meters from the ground, more kinetic energy than it started with. It's also got a little bit of potential energy when it's 2 meters from the ground because it's got a height. Now, yesterday, the practice quiz, I forgot to cancel out the masses. Didn't matter, just meant a little bit more work. Today, I'm doing that. Saves me a little bit of work. 1/2 of 10 squared plus 9.81 times 10 equals 1/2 of VF squared, 9.81 times 2 for the final height. Now what I want to do is calculate this number. When I do, I should get 148.1 equals 1/2 of VF squared. And I also want to calculate this number. That gives me 19.62. Let's take the 19.62 over by subtracting. We always get rid of what's not attached to the VF. It's 19. It's added to the VF, so we take it over by subtracting. We get 128.48 equals 1/2 VF squared. Let's take the half over. We can either divide by a half or multiply by 2. Regardless of which one we do, we're going to end up square rooting that number, and it's going to give me a value to 3 digits of 16.0 meters per second. And again, that seems reasonable. We started with a speed of 10 meters per second. When we're 2 meters from the ground, we have a speed of 16 meters per second. Of course, it's going to be faster. B, the speed of the car when it hits the ground, not much different. We should expect a little bit more than 16. Probably not much. It's not falling that much further. You got kinetic and potential energy once again at the beginning. But this time we have only kinetic at the end. Now mass only appears in one place on the right side. Doesn't matter. As long as it appears in every term, we can cancel the mass. The left side here is the same as it was in the last question, 148.1. Take the half over by dividing by a half, or you can multiply by 2, and then square root. And when we solve that, we get 17.2 meters per second to 3 digits. Check your answer. Is it reasonable? Sure. It's a little bit faster than the speed was when we were 2 meters from the ground, which is faster than when we were at the top, 10 meters from the ground. And that's it.